Up to this point, all of our applications of math induction have been on sequences and series. And in this lesson, I really want to go into one of my favorite branches of mathematics, number theory, to look at how we can use the principle of mathematical induction to actually prove divisibility rules. Before we get started on that, though, let's take a deep breath. And let's begin. So before we get into really mechanically how to use math induction to prove divisibility rules, there's a really important thing that I need to share with you about divisibility. And that's this idea that if you have an expression, like f of n, that's divisible by an integer d, I want you to know that we can write that expression, this f of n, in the form a times d, right? In other words, another way of expressing this key point is that the clearest way to write a mathematical expression about divisibility is through multiplication. So if you really want to say that 12 is divisible by 6, it doesn't make sense to say 12 divided by 6. The clearest way to show that 12 is divisible by 6 is to say that 12 is equal to 6 times 2. Right? And the reason for that is this allows me to get an equation. This, like, I have to do something like, well, 12 divided by 6 is 2, which is an integer, and we sort of have to express that it's an integer. By doing it this way, we have sort of a cleaner and quicker way of expressing this idea of divisibility through multiplication. And so a very simple example that I have of that is just here, where I say, show mathematically that 144 is divisible by 6. And I want you to use multiplication to be able to show this. Right? And so here, you might notice something like 144 is 12 times 12. But we could do a little bit of factor sharing. If I like shared one of the 2's over this way, I could make this 6 times 24. In other words, we can say that 144 is divisible by 6 by saying that 144 is 6 times some integer, 6 times 24. We're really going to be using that idea that 144 is 6 times, some integer in order to show divisibility. We're going to be using that a lot as we use the principle of mathematical induction to prove divisibility rules. So if any part of this was unclear, I really encourage you to pause, rewatch these 2 minutes, and make sure that you're comfortable with this idea that an expression like this shows the divisibility of 144 by 6. In the rest of this video, I'm going to go through and do 2 math induction problems. The first is going to be a little bit simpler, and the second will be a little bit more complicated. If at any point in this one you feel like you've got the hang of it and you want to try it out, I really would encourage you to pause the video and do as much as you can on your own. I do think that that's the best way for you to sort of test your knowledge of this. But if you really need to see it first, we're going to go ahead and go through this first one. I didn't mention in the previous slides, and I hope that it's clear from the work we've done so far, the steps in math induction aren't really going to change, right? So what is step 1 really supposed to be for us? Step 1 is supposed to be, remember, that we're writing this in mathematical notation, right? Well, saying 7 to the nth power minus 1 is divisible by 6 for all integers is not, it's mathy, but it's not really an equation. And so step 1 is really where I want to use what I was asking us to practice in the previous section. Saying that something is divisible by 6 is like saying that 7 to the nth power minus 1 is equal to 6m for some m, which is an integer. Right? By saying that 7 to the n minus 1 equals 6m, we're saying that this expression has to be divisible by 6. Another way of saying is that it's a multiple of 6. Being a multiple of 6 and being divisible by 6 are both the same thing. So now that we've done step 1, we've written it mathematically, we go on to step 2. Step 2 is where we do the work for our base case. Right? Now, the natural numbers are basically 1, 2, 3, 4. They're basically the positive integers. Okay? So my base case here is going to be for n being 1, right? So I need to show this is true for n equals 1. So show true for n equals 1. So to do this, I'd say, well, 7 to the first power minus 1 is 6. which is 6 times 1, right? And the reason I did the 6 times 1 thing is really just to exhibit the thing that we were showing in step 1. We're showing that 6 is indeed a multiple of 6. Of course it is, it clearly is, but it's nice for us to practice it here. Remember, it's really a good idea as you're going along to take a moment to sort of write a quick sentence about what you've done so far. So at this point, we've shown that our claim is true for n equals 1. We now move on to step 3. Remember that step 3 is called our inductive hypothesis. I've noticed that some of you write induction hypothesis. I've always heard it as the inductive hypothesis. And in this inductive hypothesis, we're supposed to assume true for n equals k. And so this is where we really just take our initial statement up here and we say, yep, we are going to assume that 7 to the k power minus 1 is equal to 6m for some m. Okay, great, wonderful. Remember, just like we have in all of our other induction proofs, this thing is going to be critical. We are going to have to use this in step 4. If I don't use this somehow in step 4, it means I've done it wrong, and I probably have a mathematical slip-up somewhere. Okay, so we're going to keep that in mind. Right, now let's move on to step 4 here. Step 4 is our inductive step. And in this, I want to prove that it's true for n equals k plus 1, reliant on what we had found before. So I always do something here like I want to show that 7, remember I'm just replacing the k with a k plus 1. So 7 to the k plus 1 minus 1 is equal to 6. Now, really important thing here, I don't want to use m again, because m is already like I don't expect that these are both going to be m, so I need to use something else here. I also don't want to use n because it was something that I'd kind of talked about before. So I might go here with p, or you could use j, you could use v. You just want to use some consonant, some letter that we haven't used anywhere else. All right, so in a lot of ways, the rest of this is going to go like the way that we've seen a lot of induction proofs go. I really want to utilize this somehow. I notice this has a 7 to the k, and this has 7 to the k plus 1, so maybe we could rewrite this as 7 times 7 to the k minus 1. Now again, I really just want to be working with the left-hand side here. I'm not going to write equals 6p, because that's the thing I'm trying to show and I'm trying to prove. Now, really important thing here. You may see a 7 to the k minus 1 here, but you can't replace this with this because this 7 to the k is multiplied by 7. So the frustrating thing is it's like I have the 7 to the k, but I can't really get the minus 1 because it's all disconnected. So I want to do something interesting here. If this is true, couldn't I just add the 1 to the other side and get the 7 to the k equals 6m plus 1? Like, if this is true, I should be able to make a little modification to it and get an equivalent expression. Now that I have that, I can use that over here. I can do 7 times my expression for 7 to the k, 6m plus 1, and then still have my minus 1 on the end. Right? In doing that, I can now distribute the 7 through and get 7 times 6m plus 7 minus 1. Well, that plus 7 minus 1 is going to become 6. So this is 7 plus 6m, 7 times 6m. So 7 times 6m plus 6. But remember what my goal was. My goal was to show that this was 6 times some integer p. Well, look at this. These both have a factor of 6. So just factor out 6, and there it is. This 6 times 7m plus 1 is showing that this k plus 1th expression is indeed 6 times some integer p. If you really care, that integer p is 7 times whatever m was plus 1. The important part is these are both integers. And here I decided to add a little bit of clarity. Since 7m plus 1 is an integer, we've proven our inductive step. At this point, all I need to do is go on to step 5, which is our conclusion, same as it's been for all of these other induction problems that we've done. So step 5, which is our conclusion. I'd encourage you to pause the video now and sort of think of what this conclusion should be. Remember all the components that we had before. Unsurprisingly, the conclusion looks the same as everything that we've done before. We've shown our claim is true for n equals 1, and that if it's true for n equals k, it will be true for n equals k plus 1. So by the principle of mathematical induction, it's true for all n greater than or equal to 1, and that's sort of the same as n being a member of the natural numbers, which means we've proven what we set out to prove from the beginning. So I hope that you see here that the process of using mathematical induction to prove statements for divisibility is really similar to anything else. The only difference is we do need to pay a little bit of attention to how we use our inductive hypothesis and how we might even change that expression a little bit so that we can plug it in and use it in our inductive step. That's going to become a little bit more complicated and a little bit more involved in our next example, so let's go into that one now. So in the second example, we're going to use mathematical induction to prove that 5 to the nth power minus 2 to the nth power is divisible by 3 for all n being natural numbers. In other words, n being greater than or equal to 1 as an integer. In a lot of ways, this problem is going to be similar to the last one that we did, so if you felt really comfortable with that one, I'd encourage you to try this one on your own, even if you're just one step ahead. If you do step 1 and then check in, step 2 and check in, step 3 and check in, that'll be fine. I think it's good for you to get a chance to practice this before we get to the homework when you're really on your own. So remember, we should be starting with step 1. So step 1 for us is supposed to be that we write this mathematically, right? We want to prove that this thing is divisible by 3. So that means that 5 to the n minus 2 to the n has to equal 3m for some m being an integer, right? In other words, I'm reframing this about, instead of being about divisibility, it's about being a multiple of 3. Step 2 is where we do our base case. Our base case where I'm going to show this is true for n equals 1, because that's where I'm starting, right? If n is 1, I'm going to have 5 to the first power minus 2 to the first power. That's 5 minus 2, which is 3. Sure enough, 3 is 3 times 1, which is what we wanted to show. I've noticed as some of you have gotten sort of further and further into doing these induction problems, it can be easy to start feeling like, oh, I don't really need to write that the name of the step is the base case. I don't really need to write, show that it's true for n equals 1. I don't really need to write a little conclusion. It's really a good idea to get into that habit. So please make a habit of doing that now. It's really just proper form when you're proving something to try and make it easy for anyone after the fact to read and understand. A lot of proof in mathematics is about communicating with other mathematicians, and that means you really should be taking time to make sure that your work is readable and not just a jumble of symbols. Step 3, right? In step 3, we're doing our inductive hypothesis. And this is where we're going to assume that it's true for n equals k. All right, so that means I'm going to take my initial statement and my initial mathematical writing, and I'm going to write that 5 to the k power minus 2 to the k power equals 3m. You may have realized on the other problem I said that we need to use a different letter. At this step, it's okay because I'm not planning to use this one at any point. This one I'm planning to use, so when I write step 4, I shouldn't be using m again because that m is probably going to show up here somewhere. So if you haven't done step 4, where you think about what your inductive step is, I would really encourage you to pause the video, make sure that you can write out clearly what that next step is going to be. So in step 4, I want to prove the claim is true for n equals k plus 1. I want to be able to go to the next term in line and show that that one is true, of course dependent on this, right? So I'm definitely going to be using this as I move forward into step 4. So let me write the thing I want to show. I want to show that 5, not to the k, but to the k plus 1, minus 2 to the k plus 1 is equal to 3 And I'm going to use P this time. That seems to always be one of the ones that comes to mind to me. So this is the thing that I want to prove. And I guess a part of what I'm thinking is, we sort of did the trick in the last problem where I did like 5 times 5 to the k, and maybe I'll leave the other one alone. Like maybe we'll only look at trying to change one of them at a time. We did this thing last time where we did this and we tried to replace this one with stuff that we found up above. So from this thing up above, what could we say that 5 to the k is equal to? Wouldn't it be equal to 3 to the m plus 2 to the k? So let's go ahead and use that, right? This will be 5 times 3m plus 2 to the k, and then minus the 2 to the k plus 1. Remember, my goal here is to show that this thing is a multiple of 3. That's really, really what I'm going for. So this 3 here I'm happy about. I'm going to have to figure out how to deal with some of this other stuff, right? So next, I'm thinking that maybe we distribute this 5 in. That would give me 5 times 3 to the m, or I'm sorry, 5 times 3m, plus 5 times 2 to the k, minus 2 to the k plus 1. And so I'm kind of looking at this saying, I feel good about this term because it already clearly has a factor of 3. I just need to find a way to get a factor of 3 out of this. Can you think of any way that I could factor these two terms? Is there anything that these two guys have in common? Hopefully you're noticing that this 2 to the k plus 1, I could also write this as 2 times 2 to the k. And if I wrote that like that, the neat part is these both have a 2 to the k in them. So if I were to factor that out of these two terms, what I'd have is I'd have 5 times 3m plus 2 to the k times 5 minus 2. Well, how convenient. That's 3, right? So now I have 5 times 3m plus 2 to the k times 3. I can now factor 3 out of that. Right? And remember, that's what I was going for all along. What I was going for all along was that this expression could have a 3 factored out of it. And all the way down here, we figured out, sure enough, I can factor a 3 out of this. And so here I could even write something like, since 5m plus 2 to the k is an integer, 5 to the k plus 1 minus 2 to the k plus 1 is divisible by 3. Right? Like a simple little statement like this helps you to show the person that's reading your work that you know what you're talking about. You're not just doing 5 steps and going, yay, look, I followed all the steps and I finished the thing. At each step, you're sort of talking about how we've come closer to our proof. The final step is indeed that we want to have our conclusion. Our conclusion has, as we've noticed, has gotten more and more the same, or I suppose it's just stayed the same the whole way through. Take a moment to make sure that you still remember what that conclusion should be. And there it is. So we now have a third thing that we are going to be developing practice in proving using mathematical induction. We had series, then we had sequences, and now we have divisibility. So there are a few more things in this class that we'll use it for, but this method of proof by mathematical induction is really, really a powerful tool throughout all of mathematics. There are lots of other proof methods, but this is the one that comes up often in showing and proving patterns. So I hope that as we're progressing through this, you're getting better and better at recognizing how mathematical induction works. As always, if you have questions, please ask them, and I wish you best of luck as you practice these on your own.